All right, we are going to do 4.1, which is relations and functions. So what is a relation? So a relation is a set of ordered pairs. So remember, your ordered pairs are x, y values. So it's a set of those values where x is the input value and y is the output value. Okay, so there's just some relationship between x and y, where x is the input, y is the output. The domain of a relation is the set of all possible x values for the relation. The range, the set of all possible y values for the relation. So we're going to look at a relation here. Okay, so we've got 6 ordered pairs in our relation. What is the domain of this relation? So your domain, again, is the set of all possible x values for the relation. So we're going to write our answer here for our domain in set notation. We're going to write it as a set. Okay, the relation itself is also written as a set. It's using this little squiggly bracket. Okay, so we're going to put one at the front and we'll put one at the end. So domain, all possible x values. Well, let's look at our relation. What x values do we have? We have 5, 4, 3, 2, 7, and the last ordered pair is another 4. We already have 4 written down as in the domain, so we don't have to rewrite it, and there is our domain. So I want you to pause here and see if you can figure out what the range would be. What would the range be of this relation? All right, your range is all the possible y values. So if we look at our ordered pairs, we've got 2, 1, 0, 5, 4, 3. And there is our range. We can also show our relations in a mapping diagram. And then when we put it in a mapping diagram, we have domain and range split up, okay? But the same points are still there, right? We still have the point 5, 2. It's just written right here. Okay, we have the point 4, 1. We also have the point 4, 3. Remember, we had 2 points with an x value of 4. 3, 0, 2, 5, 7, 4. Okay, so again, it's just listing all of our x values. That's our domain. All of our possible y values. That's the range. Okay, a relation can be a function. Okay, a relation in which every domain or x value, so every domain value or x value corresponds to exactly one y value or range value. That's what a function is, okay? So a relation is either a function or it's not a function. So let's look back at this relation that we had just looked at, okay? If we look at the mapping diagram, this is a function if every value in the domain goes to exactly one value in the range. This relation is not a function. It does not match that rule, okay? So majority of our domain values go to exactly one range value, right? 5 is in our domain, it goes to 2, and that's it. 3 goes to 0, 2 to 5, 7 to 4. But 4 in our domain maps to 1, 2 values in the range. So that would not be a function. So we're going to do a couple examples of determining if relations are functions or not. So we've got 2 maps here. Which of the following mapping diagrams shows a function? 1 or 2. So I want you to pause, see if you can figure it out. All right, let's talk through it. So if we look at the 2 relations, a function, every domain value is mapped to only one, or to exactly one range value. So if we look at our first relation, 1 is mapped to 6 and only 6. So still a function. 2 to 9, still a function. 4 to 12, not 4 to 12. 3 to 12, still a function. 4 to 15, it's still a function. 5 to 15, it's still a function, okay? So each x value goes to only one y value. The other relation, though, this one is not a function because of our domain value of 2. If we look at 2, 2 is mapped to 4 and 10. Okay, that's an example of what a function is not. Okay, so number 1 is a function, and I have written over here an explanation that we can use. So the first one is a function. Each domain value goes to only one range value, where in the second one, the domain value of 2 goes to 4 and 10 in the range. So 2 is not a function. So number 3, which of the following tables shows a function? Explain your answer. So another way of representing a function, but remember, a table of values is just a list of points. Okay, so we have in each table 5 points. Your x values, that's where you're going to find your domain. Your y values, that's where you're going to find your range. So I want you to pause here and think about, would it be number 1 or number 2 that is a function? All right, so if we're looking at this, we could kind of draw our own map here. So I'm going to look in my domain and see if I have any repeated x values, and I don't. So now if I just look at which x value goes to which y value, they all go to their own y value, right? There's no x value that goes to 2 different y values. If I look at the second table and I look in my domain, I notice that I have 2 written twice. So I'm just going to ignore that 2, that second 2, and I'm going to just kind of map them over. So 2 goes to 4, 0 goes to 2, 3 goes to 1, 2 again goes to this 5, and that tells me right there I have an x value that goes to 2 values in the range. That's not a function. So the first table would be a function. Our explanation, each x value has its own y value, where in the second one, the x value of 2 repeats and is paired with 2 different y values. All right, so moving on, we also have what's called the vertical line test to help us find functions. And we use this when the relation is graphed, okay? So the relation is a function if and only if no vertical line passes through 2 or more points on the graph. So if you have a vertical line going across your graph, it should only go through 1 point at a time. It never should ever go through 2 points at a single moment. If it does, it's not a function. Use the vertical line test to determine which graphed relation is considered a function. Now, you don't have like a vertical line that you carry with you. Actually, you do. It's called your pencil. Okay, so I drew a little pencil here, and I'm going to use the vertical line test. So if I look at this, I'm near the second graph, so I'll do the second graph. If I drag my pencil across, and now I've hit a point that I can see on the graph, and as I move across the graph, notice that I only ever hit 1 point at a time with my pencil. So that first one passed the vertical line test. That first one is a function. Now, if we go to the second one, and I drag my pencil across, right away when I get to a point there, I'm hitting 2 points on the graph at the same time. And I'm going to keep doing that all the way across. I'm hitting 2 points. Okay? That tells me this is not a function. So then we got 2 more questions down here. What is the domain of each relation? And what is the range of each relation? So the domain, again, is all possible x values. So the domain of, well, let's look at the first one. Call that 1. So for the first graph, your domain, possible x values, so I'm looking at my x-axis here. So I've got x, if I look at my x value here, I've got a point there and a point there. And if I look at every single x value up until -2, I've got 2 points attributed to that x value. But when I hit -2, I've got 1 point there, and then the minute I go past -2, I have no points. So that tells me that my range ends at -2. So not my range, my domain. So the domain would be all real numbers greater than or equal to -2. And that's because if I look at all the x values starting at -2 and going greater than -2, I have a y value that goes with it, that corresponds to it. Okay? Now, if we talk about the range, we're doing the domain of the second one. My bad. So the domain of the second graph, I am looking for all the possible x values. So I don't have like a stopping point to the left and right, okay? If I look at my graph, if I start at 0 for x, there is a y value, and as I move across, I continue to have y values for all these x values, and I still have x values, still have x and y values, and I have arrows that keep going up. That line, so there's arrows, so that actually keeps going and going and going forever in that direction. Eventually, it will hit every single x value that way. If you look to the left, the same exact thing happens. It's going to keep going, up, and it's going to hit every single x value to the negatives. Okay, there's no bound on our x values. So our domain for that second one would just be all real numbers. All right, so for the range, all possible y values, I want you to pause here and I want you to try that one on your own. All right, so now if we look at that, for the first graph, it's all real numbers for your range, okay? So your range is your possible y values. If I look at this graph, my y values going up, this line's going to keep going and going and going, and it's going to eventually hit all of the y values going up. Same for all the y values in the negatives. So it's all real numbers. For the second graph, the range is all the possible y values. Well, it looks like every single y value is being hit, and it will keep going up because these arrows are going up until you hit this -5. There's no y values less than -5. So our range is real numbers greater than or equal to -5. All right, last thing we're going to talk about is function notation. Okay, so I have 3 functions written here in function notation. Okay, and the way that we say these, the first one is f of x. The next one is h of x. Then we have g of x. Okay, so what does f of x mean? It means the value of the function f at x. Okay, x determines the function of f. X is your independent variable, it's still your x. And instead of y, we use f of x to show that the dependent variable, y, the output, depends on the value of x. It's a corresponding relationship. So what we're going to do down here is we are going to look at the graph of f of x to the left, where f of x is, and in your notes, it only says x squared plus 2. Change that to negative x squared plus 2. Okay, it's a graph of negative x squared plus 2. And then find each indicated function value. Okay, so f of 0. So f of 0 is the value of the function f at 0. So if we look at where x is 0 on the graph, so our function is f is 0 right here, right? Or excuse me, x is 0. What is the value of the function? Well, I go up. What's my y there? 2. So f of 0 equals 2. And that's not the only way that you could do this, okay? If you look at f of 0 and your f of x, f of 0, the function is this negative x squared plus 2. So if I plug in 0 for my x, negative 0 squared plus 2, Well, 0 squared is 0, and it can't be negative, so it's really just 0 plus 2, which is 2. You get the same thing. Okay, for f of -1, we go to where the x value is -1. So x value of -1, your y value is 1. So f of -1 is 1. You could also take your f of -1 and take it as meaning, okay, and replace the x, instead of f of x, it's f of -1. Replace the x with -1, and then simplify. So -1 squared, well, it's -1 times -1, which is +1. So it's -1 plus 2, and -1 plus 2 is 1. Get the same thing. Okay, f of 2. If you go to where 2 is x is 2 on the graph, f of 2 should be -2. If we plug that in, f of 2 is -2 squared plus 2. 2 squared is 4, so it's -4 plus 2. You get -2. All right, I want you to pause here and try these last two on your own. So for f of -2, if you look at the graph where x is -2, your function has a value of -2. If you plug it in, you also get -2. And then f of 1, x value of 1, your function's value is 1. So f of 1 equals 1. Now f of 10, if you look at your graph here, we don't see the x value of 10. Okay, but we can plug it into our function and do -10 squared plus 2. Get -10 squared is 100 plus 2, and -100 plus 2 is -98. All right, that is all that we have for 4.1.